Hi, class. I just want to take a minute and go over some of the concepts we'll be learning in Unit 2 and in the form of a couple of examples. So I'm going to kind of use this simple picture here to demonstrate some of the principles of how to solve um, these vector problems in 3D when you're given an azimuth and elevation, when you're given coordinate direction angles. We'll talk a little about the direction angle identity, unit vectors, position vectors, force vectors. So this is most of the stuff that's covered in units 2.1 and 2.2, and I'll do a separate video covering the dot product later in the week. So what we have here is just a simple vector, 3D vector in an X, Y, Z plane. So this follows the right-hand rule, right, where X, Y, and Z. One of the tricks I like to use, you'll often see, diagrams of people's fingers like this when doing the right-hand rule. But something that helps me remember it is if I point my fingers in the direction of the X-axis and then curl my fingers towards the positive Y-axis, my thumb has to point in the Z direction. So X is going this way, Y is coming out of the board, and Z is going straight up. So that's why it's drawn this way. So we're given this vector here in blue. And in this case, right here, it's presented as the direction of the vector is given in the form of an azimuth and elevation angle represented by theta and phi. And so in this problem, we're given the magnitude of the vector, the elevation angle, the azimuth angle, and we're told to find the f vector in Cartesian coordinates. So how do you solve this? In the slides and videos, they kind of give you some canned equations you can use, but we're going to talk a little bit about why those equations work. So the first thing we're going to do is we're going to look at this triangle. Let me try to outline it. We're going to look at first this triangle. And if we recognize that this is it's a right triangle, and we have this angle theta, then this side here should just be the hypotenuse, which is the magnitude f, times sine of phi, right? Basically, we're now looking at this, right? This, what we will call, you can call this fz. And I'm going to call this length right here for, I'll just call it fxy for now. So, right, we're just looking at this upper triangle, just redrawn it flat. So you can tell, right, that fz is just going to be f times sine phi, right, which with given these numbers happens to be 118.2 pounds. Okay, and then this fxy, this isn't a final answer that we're looking for, but it's an intermediate that helps us, is going to be f cosine phi, right? Which, given our numbers, happens to be 20.83. So that we've solved the upper triangle. Now we'll look at this lower triangle. Let me try to outline it here for you, where now fxy is the hypotenuse. Right, so if we draw this one, we'd get let me try to draw it flat for you. All right, so we got, this is theta, this is fxy, this is fx, this is fy, right? So I'm just trying to draw this triangle that's drawn in three-dimensional space. What happens if you just are looking straight down on it, right? And so you can tell that, okay, we got this fxy, so obviously fx will just be fxy cosine theta, and fy will be fxy sine theta, which if we go ahead and replace fxy with this f cosine theta, gets us fx equals f cosine theta, or cosine phi, sorry, because that's the value for fxy, cosine theta, right? So that's the equation, the canned equation that you've likely seen in the videos already. And then fy is going to be f cosine phi, right? Because that's fxy sine theta, because now we're looking at this triangle. And those values happen to be for fx, 11.95, and for fy, 17.07. Those are all units of pounds. And so if we were to write that in Cartesian coordinates, I could say f vector equals, there's lots of ways to write those. I kind of like the I hat, J hat, K hat, but you could do however. So it'd be 11.95 I for the X component plus 17.07 J for the Y component plus 118.2 K hat for the Z component pounds. So, and that's how you would solve that problem. So, that's how you can derive, this cosine phi, cosine theta. And you should always think about this, because it won't always be this canned equation that you see in the notes. If theta was measured over here instead, that was theta, then the equation could look differently. So knowing how to look at the two different triangles, the upper triangle and the lower triangle, and figure out how to arrive at your final equation is really important to be able to know how to do. So that's how you would solve it if it was given to you in the form of an azimuth and elevation. We also talk a lot about coordinate direction angles, which are much easier to use. So you can pause it, take a look at that if you need to catch up. We're going to solve this problem again. But this time, instead of an azimuth and elevation angle, you're going to be given coordinate direction angles. Just clean this up a touch. Okay, so with coordinate direction angles, right, what those look like is those are angles measured from each of your respective axes to your vector. So we're going to have an angle measured from the x-axis to our vector, and that's called alpha. We're going to have an angle measured from the y-axis to our vector, and that is called beta. And we're going to have an angle measured from our z-axis to our vector, and that is going to be called gamma. And in this case, we're given that alpha equals 84.3 degrees, beta equals 81.8 degrees, and gamma equals 9.93 degrees, and F is still 120. And again, we're being asked to find the F vector in Cartesian coordinates. So when you have coordinate direction angles, the way you can think about it is each of these, you basically have a right triangle in each of these sort of goofy planes. They're not in the, any given X, Y, Z plane, but it's sort of in between them all. So right, I could draw it as something like this, where I'd have, say this was that F vector, and this is my x-axis, and this would be the angle alpha, right? So if I were able to look at it at the right angle, so that this angle alpha was just in the plane, I could reorient it to look like this. And similarly for the y, right? So I could come up with something like this. Well, okay, here's my f vector. This is my y-axis, and this is the beta angle. And same thing for the z, right? So this is my z-axis. That's my f vector, and this is gamma. So does that make sense? Hopefully that. Basically, we have three separate right triangles where the angle is, the hypotenuse is the vector in question, the adjacent angle is, or the adjacent length is my axis of interest, and the angle there, that inner angle, is alpha, beta, or gamma for x, y, and z respectively. So you can see, hopefully this is starting to look kind of obvious what we're going to do, right? To find the x, y, and z components, well, these are all right triangles, so it's just going to be f cosine the angles, right? So it's as simple as saying f of x, right, is going to be f cosine alpha, which is going to equal 11.9. F of y is going to be f cosine beta, which for our numbers is 17.07. And f of z can be f cosine gamma, which is 118.2. So I am using, right, the same numbers as last time. Sorry if the glare is making that difficult. Get this thing there. Not quite so glare, just need a little bit more light. All right, so this is the exact same vector. We get the exact same x, y, and z lengths. But it's just represented in a different way. And frankly, the coordinate direction angles are much easier to use because it's just always, your magnitude times cosine. So I'll write again, if I wanted to write this as an actual vector notation, I could say 11.9 I hat plus 17.07 j hat plus 118.2 k hat pounds. Right, so that's the final answer we're looking for. So to take this one step further, imagine we were given this problem, but we weren't given gamma. So we were asked to find not only f, but also gamma. So that is actually pretty simple. So you can go ahead and pause, catch up if you need to. Hopefully this is all legible in the video. So say we're only given two coordinate direction angles, but not the third one. In that case, the way we solve this, right? So in 2 dimensions, we already know that if I have a right triangle, then x squared plus y squared equals h squared if it's set up like this, right? Pythagorean's theorem extends to 3D just fine, right? So if I have this sort of a thing where I got an x distance and a y distance and a z distance and a vector that, like that, we'll call this, rewrite this so it's a little more obvious. Right? And right? The same holds true, right? So x squared plus y squared plus z squared equals h squared, right? Pythagorean's theorem still holds true for 3 dimensions. And so, thinking about what we just saw, right? We already have solved. We already kind of know something about the x and y directions, and we know the hypotenuse length, right? Because we're given that 120. So, right, we already solved last time for fx, fy, and fz. So we know that the x component is our fx, which we can write as f cosine alpha. And so we can plug it into here, right? So that value squared plus the y value squared, which is, you know, since we haven't dealing with coordinate direction angles, it's f cosine beta, that whole value squared, plus f cosine gamma squared equals the magnitude squared, right? So f is that 120. And you'll see that, oh, hey, each of these has an f squared term. So the f's all cancel out. And I just get a 1 over here. And so what we end up with is cosine alpha squared plus cosine beta squared plus cosine gamma quantity squared equals 1, right? Which is something you probably saw in the notes already. And so now we know alpha, we know beta, we just need to find gamma, so you can do some algebra and eventually get, you know, to say gamma equals, skipping a lot of steps, it equals the inverse cosine of the square root of 1 minus cosine alpha squared minus cosine beta squared, right? And if you solve that out, you will get that gamma equals 9.93 degrees, which is what we had originally in the first problem. So hopefully that kind of helps you understand how, you know, why does this relationship exist, right? This coordinate direction angle identity, and what coordinate direction angles are, right? And how the kind of the different ways of representing 3D vectors, the direction of 3D vectors. So one more thing that we're going to talk about is we're going to talk a little bit about now unit vectors, right? So imagine then this problem was saying, you know, we don't want, so you know, find the f vector, but also find the unit vector in the direction of the f vector, right? So a unit vector is a vector whose magnitude is 1. So right, all vectors are composed of two things, a magnitude and a direction. The unit vector is essentially just the direction. It can be multiplied by any magnitude to get another vector, right? So imagine I have a vector that's 3 units long and it points that direction. It could be a position vector, it could be a force vector, doesn't, you know, it could have any number of units, but it points in this direction. And it's 1, 2, 3 units long. And I divide this vector by 3. What I end up with is a vector that points in the exact same direction, but its length is 1, right? It has no units. It's just pure direction. And I can take this vector, I know, you know, and multiply it by 50 pounds, and now I have a vector that's has a magnitude of 50 pounds that points in this direction. So hopefully that kind of helps conceptualize what a unit vector is. It's the direction part of the vector, right? That can be multiplied by any given scalar to get some new vector. So imagine this problem, they say, we want to find this unit vector. So a unit vector is just a vector divided by its own magnitude, right? Which ends up giving us a vector whose magnitude is 1. So we've already solved, you know, this force here. So I'm going to skip, you know, the steps where we would find the f vector. So we know that the unit vector is going to equal the f vector divided by the magnitude of the f vector. We've already solved for the f vector a couple of times. We know that's 11.9 in the I and then the z direction, and 17.07 in the y direction, and 118.2 in the z direction. And we divide that by 120. And so we end up getting that the unit vector is 0.099 the z direction. So that's 0.14 in the y direction plus 0.985 in the z direction, and it doesn't have units. Something interesting that you may know is that these values are the same as the cosine of the direction angles, right? So 0.099 is cosine 84.3 degrees, and 0.14 is cosine 81.8 degrees. So I'll let you chew on that, on why that's true, and see if that makes sense to you. All right, so last thing we're going to talk about here in this quick little video is position vectors. When your position vectors are just another way of representing or deriving vectors in 3D space. So we're going to use the same basic picture. We're not going to use coordinate direction angles now. Instead, now we're going to be given some XYZ distances. So let's see. So in the X direction, we're given 11.95 feet. In the Y direction, we're given 17.07 feet. And in the Z direction, we're given 118.2 feet. And we're going to call this point O, we're going to call this point A, and we're going to say F in this case actually equals 200 pounds. And so what we're asked to find is the position vector from point O to point A and the force vector that's in that same direction. So in this problem, when you're dealing with position vectors, the way you come up with the position vector is you walk from the starting point of the vector towards the ending point of the vector. So I start at point O. I'm going to walk in the X direction towards the end of the vector. So in the X direction, I walk 11.9 feet in the positive direction. I'm walking from the origin towards the positive x-axis. So x component of my position vector is 11.95 feet. Okay, now that I'm here, I'm going to walk in the y direction towards the end of my vector. I'm going to walk this way, 17.07 feet, and that is in the positive y direction. I'm walking from the x-axis towards the positive and the positive x direction, which is coming out of the board. So that's plus 17.07 in the y direction. And then I'm going to walk in the z direction towards the end of my vector. So walking upwards in the positive z direction. So that's going to be a plus 118.2. Plus 118.2. And this has units of feet. So that right there is our position vector ROA. It's as easy as that. Position vectors are typically pretty easy. You just walk from the start of the vector towards the end of the vector, from origin to end. So now though, okay, we need to get our force vector. We don't have an azimuth and elevation. We don't have coordinate direction angles in this problem. We just have this position vector. So what we're going to do is we're going to find the unit vector. We're going to find the unit vector in the direction O to A, and then multiply it by that magnitude of 200. We know that a unit vector you can take any vector divided by its own magnitude to get the unit vector for that direction. All right, so all we got to do to get the unit vector from O to A, so we just take that position vector O to A divided by its own magnitude. So the 1.95 in the numerator, and then 17.07 y plus 118.2 in the z, all divided by, and so the magnitude, right, it's just going to be the square root of the sum of the squares. So square root of 11.95 squared plus 17.07 squared plus 118.2 squared. And what does that get us? Well, as you can guess, it's going to give us the same answers we got before. 0.099 in the x plus 0.14 in the y plus 0.985 in the z. And then just to get that force vector, say the force vector is the magnitude of the vector, 200, times the direction, the unit vector. So it's 200 times that unit vector, which ends up getting us 19.8 in the x direction, plus 28 in the y direction, plus 197 in the z direction, and units of pounds. Bada bing, bada boom, there's your answer. So hopefully that's legible and you can read that okay and we're able to follow that okay. That's just sort of a quick overview and a couple of examples on how to approach these sort of problems. These are things that we'll see a lot. This is kind of some of these kind of things will be on the first exam. So if you have questions, reach out to me. Happy to go over examples or the practice problems that you're going through or the homework problems. So hopefully this is just a little, hopefully it's helpful to see how somebody else approaches the problem. So that's kind of my goal. I'll be trying to come out with these little helping videos, tutorials, examples every so often to help you along, give you some other perspectives, kind of see how my brain thinks through these problems, and hopefully it helps you a little bit. So anyways, have a good one and good luck.